Hello everyone, I'm Dr. Shen from University of Southampton. Today I'm going to talk about structured light. In the first part, I will show a series of exotic spatial structured light, mainly including my PhD works in Tsinghua University and works made in this university as a visiting researcher, and cooperated with many other international institutes. Then I will show some of my recent works of spatial temporal structured light, worked in Southampton, also with many collaborators from Singapore, Israel, and China. Structured light refers to the arbitrary tailoring of all the degrees freedom of light, amplitude, polarization, spatial mode, temporal envelope, phase, momentum, frequency, or wavelength. Many structured light beams can be produced by joint control of many degrees freedom. For example, we can combine the wavelength and the orbital momentum of helical phase to produce a wavelength and orbital momentum tunable laser as a multiplexing information carrier. We can also combine the OAM with a complex spatial pattern to obtain singularity array and vortex lattices. We can also further involve time in the control, introduce the temporal shape in vortex beam to create many kinds of structured orbital momentum paths. However, such prevailing light shaping is limited in separable state, that we treat various degrees of freedom separately in the control. The more general light shaping recently emerged as the non-separable state of light. A typical case is the vector beam, the space polarization non-separable solution of Maxwell equation with spatially varied vector patterns. For instance, the vector vortex beam shown here has the non-separable superposition of 2 degrees freedom, orbital momentum mode, and the polarization. Such non-separability has the same mathematical form as the quantum entanglement, where the states of 2 particles are non-separable, so many quantum methods can be transferred to as useful tools to describe vector beams. Well, recent advance of quantum optics has realized the entangled state with multiple particles and proved its usage in higher dimensional quantum application. This inspires us to think a question. Can we create new vector beams breaking the 2-dimensional limit so that we can simulate multi-particle entangled state using new degrees of freedom? To this end, let's have a review of vector beam. The 2 degrees freedom, polarization, and the orbital momentum mode of light can both be controlled on a Poincare sphere. If we make an inner product of them, we can get the corresponding spatially varied polarization patterns on a higher order Poincare sphere as a powerful tool to tailor vector beams with spin-to-orbital conversion. However, in this model, we only consider the azimuthal mode of spatial beam, while the full description of a laser beam requires 3 modes, 2 transverse indices, and 1 longitudinal. Recently, the theory with general SU2 transformation was proposed to deal with this problem, to generate a general structured Gaussian beam with arbitrary orders onto a Poincare sphere model, with the full orbital momentum evolution among arbitrary order Hermite-Logar Gaussian mode. More interestingly, we can further generalize such a model by the concept of coherent state. This is a well-defined wave packet composed by a set of frequency-degenerate eigenmodes. Each eigenmode is on a Poincare sphere, so the coherent wave packet is also on the Poincare sphere. In addition, the coherent state has an interesting property from quantum mechanics. The wave function distribution is always coupled with a movement trajectory of a classical oscillator. Based on this property, the coherent state structured light has a corresponding effect of ray-wave duality. The mode pattern is always coupled with a set of rays. Such ray-wave panchaeosphere opens new degree of freedom to describe light. The frequency ratio, omega, describes how many rays in the structure. Orbital momentum, how twisted is the ray trajectory, or how large is the acoustic range. And the coherent phase, phi, how is the ray sequence distributed in the acoustic. How to generate. The ray wave structure light can be directly generated from a laser cavity. The omega can be controlled by tuning cavity length to geometry of bouncing back and forth with multiple periods, corresponding to various ratios of longitudinal and transverse modes. The phi can be controlled by selective position of the bombing spot in the laser crystal, revealed by, for instance, the W-M-shaped opposite shape for the orthogonal phase state. But in previous work, we can only generate one trajectory mode in a cavity. We recently proved that we can excite two trajectories with the orthogonal phase state simultaneously in a single cavity. It requires a precise control of bombing spot at the location where the two trajectories modes share a same reflecting point. We successfully generated such hybrid trajectory mode in experiment, agreeing with our theoretical prediction. Especially, we used the C-cut anisotropic crystal as the gain medium, which has an inclined angle-dependent barrel fringes effect. That means the two trajectories, the larger and the smaller one, can be supported as different polarization modulations, and the hybrid trajectory as a result is controlled by the bombing displacement with diverse vector state. For the orbital angular momentum, we can also use a pair of cylindrical lengths as an astigmatic mode converter to introduce orbital angular momentum. And the planar hybrid ray-wave mode can be transformed into twisted vortex ray-wave mode with very pretty polygonal star shape. The shape controlled by the off-axis bombing displacement. Here we show the spatially twisted distribution of the hybrid ray-wave vector beam. Also, we use the anisotropic crystal and selective bombing to obtain various non-separable states, including orbital angular momentum trajectory non-separable scalar beam and the OAM-Trajectory-Polarization non-separable vector state. They have diverse topological phase distributions from star shape, flower shape, and a multi-singularity vortex shape. The study of phase allows us to break the limit of cavity to design the digital hologram to generate increasingly complex ray-wave mode, the higher-order trajectory modes, such as the lysodraws and trichoidal curved mode, that further create new degrees of freedom for complex light structure. As another degree of freedom in previous works, we can generate planar trajectory or circular trajectory carrying orbital angular momentum. But here, we can also introduce astigmatic degrees as a new degree of freedom to control the more general trajectory evolve from a linear sports array into a circular sports array as the astigmatic hybrid trajectory state. Also, previous multi-rate control are all at the degenerate state. If we can precisely control the cavity length slightly deviate from the pure degenerate state into a precise degenerate state, we can observe the multi-sport shape can be connected to a polygonal shape to create a polygonal vortex beam. So the precise degeneracy is another degree of freedom. Okay, now we know that the ray-wave structure light can open many new degrees of freedom to control light state. Let's think another question. How to control the light in higher dimensional space spanned by the multiple new degrees of freedom? For instance, in quantum mechanics, the 2 degrees of freedom of photons can realize the 4D control of the 4 Bell state as basis. The 3 degrees of freedom can realize 8-dimensional control by GHZ state as basis. Recently, we realized the full high-dimensional control based on our new super degrees of freedom ray wave laser, together with external intensity and phase tuning device by a spatial light modulation system. We can actually control the light in 8-dimensional state with 3 degrees of freedom. Oscillation direction, positive and negative, round trip location, first and second, and the polarization. Amplitude and phase of each ray state can be modulated on demand, and the light state can be controlled into arbitrary state in 8-dimensional space. For example, the GHZ state, the maximum entangled state in 3-party type. Moreover, we propose the state tomography measurement for our new high-dimensional light akin to the quantum tomography measurement, whereby the quantum static measure is replaced by the classical coherent fringes measure here. Applying the quantum-like measure method, we can also construct the density matrix for each experimental classical GHZ state and calculate the fidelity to evaluate the beam quality. All our experimental results show high fidelity to the ideal GHZ states. Here are the results of density matrices for all the 8 GHZ states, theoretical and experiment. The quantum method to characterize 3-particle entanglement can be fully used to characterize the behavior of a higher dimensional structure light in classical range. This model is easily extendable to reach even higher dimensional cases. By exploring the orthogonal momentum of a ray wave packet, we can exercise 4 degrees of freedom, 5 degrees of freedom in even higher dimensional control of light. Then I will introduce the classically entangled model from spatial domain into space-time domain, a novel structured path with space-time entanglement. Light mode are traditionally solved from Maxwell equation as a space-time separable solution, including the complex vector beams. There is another family of space-time non-separable solution for characterizing structured field cycle pulses. A typical example is the toroidal pulse. Such pulse with toroidal topology has many non-trivial properties, in contrast to the transverse wave in free space, with the analog behavior of an electric dipole excitation. But the toroidal pulse is corresponding to the toroidal dipole excitation. Moreover, the pulse is propagating, so also named as Flying Doughnut. It provides the possibility to create the superposition of the toroidal dipole and the conventional electric dipole. As a result, a very novel non-radiation mode, the anapole, can be created, showing the great importance in light-matter interaction. Let's have a look at the basic property of the amazing toroidal pulse, the Flying Doughnut. Such pulse is a focused single-cycle pulse, where the electric or magnetic field form the toroidal solenoid structure in each optical cycle. Upon propagation to the focus, the pulse can evolve from a 1.5 cycle from the Rayleigh range to the single cycle at the focus. Due to the space-time non-separability, the pulse shows spatially varied spectrum. An isodiffraction effect is shown in the spectrum, that various frequency components diffract at the same rate. That means that the blue component is always confined inside and the red is always outside upon propagation. The unique isodiffraction of the pulse allows us to define two classical states to describe it. First, spectral states. The monochromatic component of light defined by specific wavelengths and with defined radial position of its peak intensity. Well, the spatial states are the general polychromatic state of light located at the position with defined radial ratio resulted from the theoretical isodiffraction relationship. For an ideal toroidal pulse, the two states are perfectly overlapped and non-separable. That means the perfect toroidal pulse can be expressed as the space-spectral non-separable state, similar to a Maxwell entangled state. On the other hand, conventional wideband pulses do not have this property. We know various colors can be diffract at different focus degrees. For example, such a wideband Gaussian beam superposed by many monochromatic Gaussian modes with similar intensity profile, but the spatial and spectral states are randomly intersected in its propagation. The general space spectral state cannot be an entangled state. With such a quantum-inspect picture, we can borrow some useful tools from quantum mechanics to characterize the classically entangled pulse for quantitatively measure the quality of a toroidal pulse. The first step, the state tomography. We measure the inner product of each combination of spatial and spectral states, which are regarded as the coefficients of various decomposed spacetime states. Next, we can reconstruct the experimental entangled state and its density matrix, then borrow the concepts from quantum mechanics to characterize the quality of the entanglement. The classical entangled states, such as the fidelity to measure the similarity of two quantum states, and the concurrence and the entanglement of formation to measure the degrees of non-separability in the entangled state. Here are the measures results for an ideal flying donut toroidal pulse, a flying donut with noise, and a wideband LG beam, and a monochromatic LG beam. The perfect flying donut is set as the ideal so that the fidelity is 1, and the fidelity decreased into 0.7 for the noised flying donut. Well, the LG beam fidelity is near 0 because it do not have a space-spectral coupling. The concurrence and entanglement formation of the flying donut is nearly 1, and that's decreased for the noised flying donut and further decreased for the LG modes. As an extreme case of the monochromatic beam, the concurrence is 0. It's a pure spacetime separable case. We recently successfully generated the toroidal pulse by conversion of an ultra-short linear polarized pulse into a two-stage process. This involves the linear to radial polarization conversion of an input pulse, followed by a spatial spectral modification of the pulse by a metasurface. The experimental optimized pulse reached a fidelity of 0.8 and a concurrence of 0.99. We can argue the experimental pulse very approach an ideal toroidal pulse. Before going to introduce more intriguing topological properties of toroidal pulse, let's have an introduction of Skyrmion. The structure of which can be understood as the unwrapping of a spinning vector sphere onto a 2D plane. The topology of Skyrmion is characterized by the Skyrmion number that reveals how many times of the unwrapping from the spinning sphere, and that can also further separated into 3 topological parameters to describe the finer structure: the polarity, vorticity and helicity. And here shows some examples of the configurations with diverse topological numbers. And recently, it's a very hot topic to study the Skyrmionic configuration in optical field. Okay, the toroidal pulse is a Skyrmionic pulse. Here is a magnetic vector field distribution of a toroidal pulse at focus. Due to its non-transverse effect, there are singularities in the field, and we can observe two Skyrmions with different textures in the magnetic field as the front and the tail of the pulse. In order to observe more topological Skyrmions, we present such a generalization of toroidal pulse towards the supertoroidal pulses. In the conventional process to solve the Flying Doughnut pulse, we use the finite energy assumption into the localized energy transition model, and the finite energy parameter is always fixed as 1. Here, we consider the general cases with the finite energy confined factor alpha larger than 1. When we increase the value of alpha, we can obtain the supertoroidal structure with the increasing complexity of electromagnetic field, akin to multiple toroidal structure like the matryoshka. Here, I will show that the supertoroidal pulse can hold such Skyrmions in its magnetic field. For the fundamental toroidal pulse, there are two Skyrmions with different topologies as the head and the tail of the pulse. With the increasing of supertoroidal order, more singularities are involved into the field. That allows more Skyrmions to be observed as the C3, C4, C5, C6, the 4 different planes for 4 different Skyrmions. It's with different topological textures. This is the first time the optical Skyrmions presented in the propagating electromagnetic pulse. If we increase the supertoroidal order to even higher level, the matryoshka effect goes toward infinity, so as to induce the fractal-like patterns of electromagnetic singularities. The left side shows the 20th order supertoroidal. The electric singularity shells were arranged as the self-similar pattern, the fractal-like pattern. It seems infinity when we zoom in to look it. The right side shows its magnetic field. The Toroidal and the vortex point arrays were emerged as the periodic sequence. Such fractal-like magnetic field allows the easy observation of even finer structure of Skyrmions. We illustrate the results as the full plane as the head of the pulse. Importantly, we can observe sub-wavelength features of the Skyrmions. Here, the wavelength means the optical cycle of the pulse, noted by Q1. The closer to the pulse center, the stronger the sub-wavelength effect it has. As shown in C4, the Skyrmion at the head of the pulse has multiple reversal vector distribution along radial direction due to the matryoshka effect. Then each reversal is localized in a deep sub-wavelength displacement at a level reaching Q1 over 50. This shows great importance to be used in ultra-precise metrology and imaging. As a perspective of future works on this, there are many generalized quasi-particles beyond the Skyrmions. For example, the bimeron, which can be understood as the unwrapping of an inclined spinning sphere, in contrast to the Skyrmion, that's a normal spinning sphere. That will introduce more complex topological textures to be controlled in light, if we can realize the optical bimeron. Okay, in summary, for the spatial structure light, we propose the classical entangled state can ghost higher dimensions, analogous to the multi-particle entangled state. And the hybrid railway structure enables the multi-degrees freedom control in vector vortex spin, more than 2 degrees freedom. And such higher dimensional structure can be created directly from a simple laser and controlled by digital hologram. For the spatial temporal structure light, we show toroidal pulses are single-cycle, Antipole-like, non-transverse, and space-time non-separable solution to Maxwell equation. And we propose the state tomography method as a useful tool to quantitatively measure the space-time non-separability of light. And such toroidal light pulse was experimentally generated. As a generalization of toroidal pulse, the supertoroidal pulses exhibit topological Skyrmions and fractal-like singularities, very interesting for the future exploration of light-matter interaction, communication, metrology, and imaging. And finally, welcome to follow my website to find more information of my recent researches. And thanks very much for your attention.